So we are going to continue on in chapter 7. We are continuing on to look at roots, radicals, and root functions. But in this one, we're going to talk about using exponential notation. So sometimes writing things as a root isn't the nicest form for what we're trying to do. So we want to be able to translate back and forth between the root form and the exponent form. We're also going to be able to define and use expressions with a fractional exponent. And the fractional exponent is really closely related to what happens in number 1. Then we're going to be able to convert between the radical and the rational exponent, and we're going to be able to simplify those with the rules of exponents. So the first thing we need to talk about is how to create exponential notation for roots. So in order to create exponential notation for roots, we take the number in front, n, that we've been talking about, the root number, and it becomes a fractional exponent of 1 over n. So a square root, remember, we won't have the n number written beside it, but we know it is 2, so it would be 1/2. A cube root would be 1/3, and a fourth root would be 1/4. So it's a pretty easy conversion factor when you just want to go from the root to the actual exponent, and we're going to be using that index value n for the radical to do that. So let's kind of look at this. If I have a 1/5 exponent, my index is 5, which means it's the 5th root. If I have an 1/2, my index is 2, and remember, we don't write the 2, it's implied. If I have negative 81, 81 to the 1/4, this is important, that negative is considered in front, so it remains in front of the 1/4. But if you look at D, the negative is inside of parentheses, which means it is under the roots. And my root is an even number, so this does not exist, it's not a real number. Again, in E, the negative is inside the parentheses, so it's under the root, but it's a third root, and that's okay. The third root of negative 64 is negative 4. And guys, if you're struggling with these roots, remember you can use your calculator. If you're not the arithmetic genius speed math person, definitely use a calculator to work with it, but make sure you're entering the parentheses with the negatives as they're shown on this slide. Now, for f, when we have a fraction, the root goes to the top number and it goes to the bottom number. So this would be 1 to the 1/3 divided by 27 to the 1/3. So I'm essentially looking at the cube root of 1 over 27. The cube root of 1 is 1. The cube root of 27, if I type that in my calculator, it is 3. So when you're typing this in your calculator, you can enter them as separate roots, or you can enter them with the parentheses in there. Now we're going to take it a step further, and so instead of 1 over n, we're going to have a value we call m over n. So the value m is coming from anything that is raised to an exponent with my roots. I have two things happening. I have a root, and there's an exponent under the root. So if I have 25 to the 3/2, we know the 2 is the index of my root, and the 3 is it's being cubed. So I'm taking 25 to the 1/2 and I'm cubing that. So I have the square root of 25 cubed, which would be 5, because the square root of 25 is 5. 5 cubed is 125. So these require a lot of steps, guys. If I have b, I have 3 in the denominator, which means my index of my root is 3. So it's 27 to the 1/3 squared. I can find the root of 27 by saying, okay, 27 to the 1/3 is the cube root of 27. Then I'm going to square it. I'm going to go on my calculator. I know the cube root of 27 is 3. 3 squared is 9. So it's a lot of steps, guys. Negative 16, the negative is in the front, not the parentheses. It remains out in the front. My 2 is the denominator, so I'm basically taking that numerator and I'm putting it outside the parentheses. The square root of 16 cubed, I know the square root of 16 is 4. 4 cubed is negative 64. So notice I'm basically taking the parentheses and simplifying that. Then I have part D. I have the cube root of negative 64. That negative is inside the parentheses, which means it's inside of my root. I can have a negative number if it's cubed because it's odd. The cube root of negative 64 is negative 4, but when I square that negative 4, I'm going to get positive 16. So that's where the lab will get you, is with making sure you're writing your parentheses correctly with the negatives. Again, the negative is inside the parentheses, which means it's under my root, and immediately I run into a problem because 2 is a square root. I cannot have the square root of negative 36. It is not a real number. So right there, you have to stop. So there's a lot of steps involved in these types of problems, and it's really important for you to show every single step in your work. Now if I have a negative exponent, so that's what's different here, is we're looking at negative m over n. I'm going to take what we call the reciprocal. So instead of just having that negative exponent, I'm going to do 1 over the entire statement. In the lab, it will not accept a negative exponent as a final answer, ever. So you're going to have to use this process. So I have 81 to the negative 3/4. Before I can address the root, the exponent, any of that, I need to write it as 1 over 81 to the 3/4. Now I'm going to apply what I saw before, and I'm going to do the 4th root of 81 cubed, which I find the 4th root of 81 first. I'm going to use my handy calculator because I'm not sure. That's 3. Then I'm going to take care of that 3 cubed, which is 1 over 27. And 36, I have a negative. First thing that has to happen is that negative has to be cleared out. So I do 1 over. Then I'm going to have the square root of 36 because the denominator is 2. I'm going to find the square root of 36. That one's not too bad. That's 6. 6 cubed, type it in my handy calculator, that's 1 over 216. So we're basically simplifying these expressions to get rid of the negative exponent and to get rid of the actual fractional exponent. So notice all of my final answers don't have any exponents in them. Now this one is the same thing, except for we treat this as 64 to the negative 3/2 divided by 25 to the negative 3/2. When you do 1 over this, it creates the reciprocal where it just flips it. So if you have a fraction with a negative exponent, you flip the fraction. And you can prove this algebraically by doing 1 divided by 64 over 25 would be 1 times 25 over 64. You could prove it. Or you could remember the rule. If I'm taking the negative exponent of a fraction, flip it. Then I'm going to write that as the square root of my item cubed. The square root of 25 is 5. Square root of 64 is 8. And then I'm going to do 5 cubed, 8 cubed. And that gets me to my final answer. So this isn't too bad if you remember the quick trick when you have a fraction of flipping it. And you can do 1 over when you don't have that. So now we're just looking at alternative meanings, okay? So I could write a to the m over n as what we've been doing, the root and then the exponent outside. Or I could write it as the exponent inside and the root on the outside. It doesn't matter. Either one is acceptable. And that's all this is saying, is it could happen backwards, essentially. So if I want to convert between a radical and a rational exponent, I want to be able to go both ways. So in here, we're going to take and we're going to write them as radicals. 19 to the 1/2, my index is 2. Remember, when it's 2, it's implied. Don't write it. 11 to the 3/4 could be written as the 4th root of 11 cubed, or I could write that as 11 cubed to the 4th root. Either way is fine. 14 is not a part of this 2/3 exponent, so 14 is outside the parentheses. And then I have the index of 3 and an exponent of 2. Now I have 2 terms here that I'm working with, so I'm going to deal with each one separately. The 5 stays out front, the index is 5, so I have a 5th root cubed. Minus the 2 is inside the parentheses, so I have the 5th root of that cubed. And so this difference between the 5 being out front and the 2 being inside comes from the fact that the 2 is inside these parentheses and the 5 is out front here. Now in E, I have a negative exponent. You gotta do the 1 over. Now that I have the 1 over, my index is 7, so it's the 7th root. And I have 7th root of x to the 5th. So that one is missing on the slide. So this should be 1 over the 7th root of x and then parentheses to the 5th. This is a cube root. My index is 3. And both items are in the parentheses. So this should be the cube root, and that's a typo. That should be x to the 3rd plus y to the 3rd. So I apologize for that typo. Now we want to go backwards. Let's write it as an exponential. So what is the index in G? There's no number written, so the index is implied to be 2. So that would be 1 over 2. In H, my index of my radical is 4, so my denominator is 4. My m is the exponent of 8. So this would be 9 to the 8 over 4, which does simplify because 8 divided by 4 is 2, and then 9 squared is 81. Why did I simplify this to 81 and not go further with 37? That's because 37 is not a square root that is even. It's not a whole number. So I don't really want to take that any further. I took this one further because I can easily find 9 squared. In I, my index is 8, so my denominator is 8. My exponent under the root is 8. So I get z to the 8 over 8, which is z to the 1. So now we're going to apply the rules for exponents that you learned back in elementary algebra to our rational exponents. These are all the rules for exponents. If I multiply two bases that are like, I add their exponents. If I have a negative exponent, it's going to be what we practiced, and it's 1 over the value. If I divide two like bases, I subtract their exponents. If I take something in parentheses and I raise it to an exponent, just like we did earlier, and it's negative, you flip the fraction. So we saw that happen earlier. If I have a value raised to a value, I multiply. The distributive property is at work here. If you have more than one thing in the parentheses, the exponent goes to each item. Same thing with division. The exponent goes to each item. And then this is kind of a repeat of what we've already seen with a to the negative r, but I can write that as 1 to the r divided by a to the r, but 1 to any power is going to be 1. So that's why it's in there twice. So let's look at this. In part A, I'm multiplying two like bases. A base is 3. So from my rules, when I multiply like bases, I add the exponents. If you are not great with fractions, you can pull up your calculator and type in 1/2 plus 1/3. That's absolutely okay, which would be 3 to the 5/6. So you can skip that common denominator process if you struggle with fractions. I'm perfectly okay with that. Then in part B, I'm going to have like bases that are divided, which means I subtract the exponents. Again, if you're not great with fractions, go to calculator, type in 2/3 minus 4/3. Then we have to get rid of the negative exponent. This is the biggest issue I see in the lab. 7 to the negative 2/3 is not an acceptable answer because you cannot have a negative exponent in a final answer. So you have to use that property to get rid of the negative exponent and do 1 over it. Now in this one, there's a lot of things happening, right? I have a like base of division, and then I'm raising everybody to the 6th power. You could go about this problem in 3 different ways off the top of my head. Whatever way you choose is what's easiest for you. What I like to do is I like to simplify what's in the parentheses first before I distribute that 6. So I have like bases that are divided, so I would subtract the exponent. So 2/3 minus 1. Again, if you're not great at fractions, type in 2/3 minus 1. That's negative 1/3. And again, we could take that negative away, or we could distribute the 6. It is your prerogative. Here, I distributed the 6. I just think it's nicer to do that before we get rid of negative exponents. I like to get rid of my negative exponent in the very last step of every problem. So I'm going to simplify 6 divided by 3 is 2. Same thing here. Now I'm going to get rid of that negative 2 and write it as 1 over b squared. Well, if I have a squared times 1 over b squared, that would be the same as a squared divided by b squared. This is another problem where I have a whole lot going on. So what I would do first is simplify the subtraction that happens of my like bases. You could distribute this first. What I would probably do on my own is I would do 3 minus -2 and -4 minus 1/5. But for the purpose of this PowerPoint and recognizing that all students think differently, I'm going to show the reverse and distribute the -1/2 first, because in the last problem, I did the parentheses first. So you can distribute that -1/2 to every single term. When I have this, I multiply. So 3 times -1/2 is -3/2. -4 times -1/2 is +2. And guys, if you struggle with this, please feel free to use a calculator, okay? So this is just reversing what I did in the last example and getting that negative exponent distributed to everybody first. I would do the subtraction before I clear out a negative exponent. Like I said, if there's a negative exponent, I deal with it at the end. So -3/2 minus 2, and then I have 2 minus -1/10. Again, calculator is your best friend. I have a to the -5/2. I got to write that as 1 over a to the 5/2. When I have b to the 21/10 times 1 over a, this combines into this total fraction. Taking these problems step by step is going to absolutely be key. So here, this is where the problem happens with exponents. I cannot add r to the 3/5 plus r to the 8/5. That is not okay. They're not like terms. They can't be combined. They don't follow an exponent rule. So the only thing I can do here is to distribute the r to the 2/5 into each term in my parentheses. And when I distribute it in, I'm multiplying like bases. So when I multiply the like bases, I'm adding the exponents. I simplify it. I get my final answer. You cannot combine r and r squared. They are not like terms. They have different exponents. Okay. Here are some additional problems we can look at. To work these problems first, you're going to need to write them as fractional exponents. So whenever you're given something as a root, you want to write it as a fractional exponent. Now I can use my exponent properties, and I can multiply these items by using the exponent rule for multiplication. So when that happens, I add my exponents. And I get 19 over 20. Again, if you're not great with the common denominator process, feel free to go ahead and do it with the calculator. And B, same thing. First thing I have to do is write fractional exponents. I get my fractional exponents written. Now I can apply the property. I have like bases being divided, which means my exponents are subtracted. C is kind of tricky. It does pop up in the lab. I have a root of a root. So it's like nesting dolls, right? It's like they're nested inside. So I'm going to write the first root out first. So I have x to the 1/6, the cube root of that. This would be what's inside my root to the 1/3. This is an exponent property. I'm going to multiply these two fractions together, and then that's my final answer. Again, it's your final answer as long as there's no negative in the exponent. And that is the end of 7.2. I know these lectures are kind of long. You can pause them. I know I talk fast. It's for the sake of keeping these to a decent time length. Feel free to pause the video and go back to any problem so that you can digest the information in a little more slow of a manner.